Hello. So in this video, we are going to tackle the chain rule. So the chain rule is how we are going to handle compositions of functions. So this sort of idea, composition of functions, is just incredibly broad. In fact, it's sort of so general that it's really difficult to tackle this in terms of finding a rule for derivatives without being really general, because there's really, you basically know nothing. There's no guaranteed power or guaranteed function type. It's really abstract. So what we're going to do is we're going to sort of just, as we usually do, consider this f of x and g of x as standard functions. And our goal is to take a derivative of f of g of x, right? Just taking a composition. So as usual, we're going to try putting it into the difference quotient and sort of see what happens. And we get this thing, which is sort of pretty difficult to sort of do anything with, right? Like there's not an obvious way of creating a bridging term like when we try to do products. There's no limit laws that really work here in any kind of sensible way, or at least not obviously. So before we sort of continue, as we sort of often do, we're going to sidestep for a second and do a different part of this. But even before I can start that, I'm going to sort of introduce a slightly different way of looking at our difference quotient. So this is admittedly a little bit strange, but what I'm going to do is take this sort of, again, this is not necessarily specific to composition. This is just a different way of looking at a general difference quotient. And I really want to do this to emphasize the idea of this sort of how the inputs here, this u and this v, correlate to the things in the bottom, the pieces that are in the denominator. So the way I sort of want to read this thing is that I'm looking at f of thing 1 minus f of thing 2 over thing 1 minus thing 2, right? So the idea is that the input here is exactly the same thing that's in the beginning of the denominator there, and the input over here is exactly the same thing that is in the denominator over there, okay? We usually think of these things as, as variables or things, but there's no reason we can't do functions or other sort of more creative ideas for this, and this is what we're going to need, okay? So with that, let's tackle the alphabet soup that is the algebra involved in this rule. So starting with our sort of basic difference quotient, right? This g of x plus delta x minus this f of g of x. I'm going to take that same thing, but I'm going to multiply by 1 cleverly. So in particular, I'm going to use this g of x plus delta x minus g of x. So again, why? Well, as we'll see in a minute, again, the unsatisfying version is that, quote unquote, it works, but really the hint is that that is the inputs that are happening up here, right? So I have g of x plus delta x and g of x here, and so I kind of want that in the bottom over here, but I can't do that for free, so if I do it in the bottom over here, I'm going to have to do it for the top as well, okay? But now that I've multiplied by 1 cleverly, I can switch the denominators, right? Multiplication is commutative. So I took the denominator that's over here and moved it to the left, the one that was over here and moved it to the right. So that helps me with these grouping of terms. And now I'm going to do that substitution that I talked about. So I have u, I'm going to just sort of denote this g of x plus delta x as u, and this v, I'm going to denote g of x by v and do that substitution over here, right? So I had f of g of x plus delta x, g of x plus delta x I'm calling u, so that I replaced it, so I have f of u, right? Same over here, g of x I replaced with y's, g of x I replaced with v, so I have f of v. Similarly, right, in the bottom, so I have u minus v. Now, noteworthy, right, I still have delta x going to 0, so that's an issue, right? My previous version needed that it was u going to v, but that's exactly what I have on this next part, right? So here I can notice then that is because delta x is going to 0, g of x plus delta x is going to g of x. But that's literally what, right, u and v are, so that's telling me that u is going to v, so I can replace that limit piece here. Okay? And this I haven't really touched. It's just sort of hanging out. But, you know, noteworthy, right? I split the limit because these things are both things that exist because they're both derivatives, as we'll see. So, in fact, right, here we go. So this first one was exactly that limit law, that alternate form, right, of derivatives. This one over here, also the difference quotient for just g. So I can replace it as f prime of v, right? That's what our definition was. And g prime of x, because that's exactly what this piece was. But as we recall, right, my original thing was just in terms of x. I don't want a v there. So my next step is to substitute v back in, right? V was just g of x. So that's exactly what I'm going to put down here, right? And this gives me my chain rule. In particular, if I take the derivative of f of g of x, I get f prime of g of x times g prime of x. So to be clear, f prime, so I'm taking the derivative of that outer function, but the input is still the same, right? I'm not taking the derivative of g in this section. So it's f prime of the full g of x, then I multiply by g prime of x. So this is an important distinction, and we'll have a bunch of example videos and things to go through all of those to show exactly how that works. But this sort of is the takeaway, is that g is not having a derivative when it's inside f, but on its own it does. Okay? So this is our chain rule. So we have sort of this thing, but it's sort of, it looks kind of weird, right? Like we're going to be using this a lot, all the time, really, when we're doing applications later on, because the chain rule is one of those things that once you learn to see composition of functions, you can see them everywhere. Everything is a composition of functions, and so everything involves a chain rule. But there's no sort of direct correlation between limit laws and this thing. So it's sort of difficult to think, like, why is this? I mean, like, we algebraically proved it, so yeah, okay, I guess it is a thing, but why, right? We've been sort of harping on visually seeing a lot of this stuff, so how can we understand this? So it turns out that although it is unintuitive from a limit law standpoint, it actually makes a lot of sense from a more geometric perspective. So that's what we're going to look at next. So far, we have thought about rates of change primarily as the slope of a line on a graph. This certainly has some advantages, like making the algebraic definitions of things like derivatives a lot more accessible. But it isn't the only way to think about rates of change. Another, more intuitive way of thinking of it is using physics. Let's consider for a moment a person walking around. Now, we can think of the rate of change as being the speed of our person at any given moment. But what happens if we give our person walking around stilts? We'll make the legs much longer, thereby covering more ground for the same leg span, effectively making the distance traveled for the same period much larger. At the same time, when the person is standing still, the person's speed is still 0. Thus, the stilts have magnified our rate of change. It isn't additive, it's multiplicative. The person has a rate of change, their speed, at any given time. This corresponds to the inner function in our chain rule, the original rate of change. But then we augment that rate of change with an outside force, in our case, the stilts. This is the outer function, whose effect is applied to the inner function. Finally, as we observed earlier, the stilts have a multiplicative effect on the speed of the person walking. And so, these two pieces are being multiplied. Thus, our chain rule gives us that the derivative of f of g of x equals f prime of g of x times g prime of x. So, what did we learn? So, taking a derivative of a composition of functions turns out to have this sort of surprisingly elegant rule, the chain rule. But, unfortunately, that chain rule is not all that intuitive from a viewpoint of limit laws. But, maybe surprisingly, it turns out to be really intuitive when we think of it as this sort of rate of change bit, right? So in particular, what the chain rule is sort of showing us is that the rate of change is magnified by the composition process. So if we sort of tweak the rate of change inside a function, then that outer function is just sort of magnifying that whole process. And we can think of that as exactly this multiplicative relationship, right? So what we're thinking of is that, like, if we're tweaking, a part of this, then the other part is sort of magnifying that process, just like we saw in our little, animation bit. Okay? So that is that.